Welcome to this video on the physics of light, focusing on reflection and refraction for Class 10. Light is a form of energy that allows us to see objects. It travels in a straight line, and when it reflects off objects and enters our eyes, we perceive them. Common light phenomena include shadows, the formation of images, and the twinkling of stars. Reflection occurs when light hits a polished surface, like a mirror, and is sent back. The laws of reflection state that the angle of incidence equals the angle of reflection, and the incident ray, reflected ray, and normal all lie in the same plane. Images formed by a plane mirror are erect, the same size as the object, and appear at the same distance behind the mirror. These images are virtual and laterally inverted. This diagram illustrates the law of reflection, showing the incident ray, the reflected ray, and the normal at the point of incidence, where the angle of incidence equals the angle of reflection. Spherical mirrors are part of a hollow sphere and come in two types: concave and convex. A concave mirror curves inwards and converges light, while a convex mirror curves outwards and diverges light. In spherical mirrors, a ray of light parallel to the principal axis will pass through the focus for a concave mirror, or appear to diverge from the focus in the case of a convex mirror. Conversely, a ray of light passing through the focus of a concave mirror, or directed toward the focus of a convex mirror, will emerge parallel to the principal axis after reflection. A ray passing through or directed toward the center of curvature will reflect back along its original path in both concave and convex mirrors. When a ray of light is directed obliquely at the pole of a mirror, it reflects obliquely, ensuring the angle of incidence equals the angle of reflection with respect to the principal axis. For a concave mirror, when an object is at infinity, the image is formed at the focus. It is highly diminished, real, and inverted. When the object is placed beyond the center of curvature, the image forms between the center of curvature and the focus, appearing diminished, real, and inverted. If the object is placed exactly at the center of curvature, the image is also formed at the center of curvature and is the same size as the object, real, and inverted. When the object is between the center of curvature and the focus, the resulting image is formed beyond the center of curvature and is enlarged, real, and inverted. Finally, when the object is at the focus, the image is formed at infinity. It is highly enlarged, real, and inverted. When the object is placed between the focus and the pole of a concave mirror, the image is formed behind the mirror. This image is enlarged, virtual, and erect. Moving to convex mirrors, if the object is at infinity, the image is formed at the focus behind the mirror. It is highly diminished, virtual, and erect. When the object is placed between infinity and the pole of a convex mirror, the resulting image is formed behind the mirror, appearing diminished, virtual, and erect. Concave mirrors have many practical uses. They are commonly used in torches, vehicle headlights, and searchlights to direct parallel beams of light. They also serve as shaving mirrors for larger reflections and are used by dentists to view enlarged images of teeth. Convex mirrors are used in vehicles as rear-view mirrors because they provide a wider field of view and always form erect, diminished images of traffic behind the driver. When performing calculations, we follow the Cartesian sign convention. Distances measured in the direction of incident light are positive, while those against are negative. Heights above the principal axis are positive, and below are negative. The mirror formula relates the focal length, object distance, and image distance. Here, f is the focal length, v is the image distance, and u is the object distance from the mirror's pole. Magnification for spherical mirrors compares the size of the image to the size of the object. It is defined as the ratio of image height to object height, or negative image distance divided by object distance. Let's look at some practice problems. If a spherical mirror has a radius of curvature of 20 centimeters, its focal length is simply half of that, which is 10 centimeters. Similarly, for a convex mirror with a radius of curvature of 32 centimeters, the focal length is 16 centimeters. In this problem, a concave mirror produces a 3 times magnified real image. Using our magnification formulas, we can determine the location of the image based on the object's position. To obtain an erect image with a concave mirror, the object must be placed between the focus and the pole. In this case, the image will be virtual and larger than the object. This slide is intentionally blank as a placeholder for your diagrams. For an object placed 10 centimeters from a convex mirror with a focal length of 15 centimeters, we can use the mirror formula to calculate the exact position and nature of the resulting image. Finally, a magnification of +1 for a plane mirror means the image is exactly the same size as the object and is erect, as the positive sign indicates a virtual image. Moving on to practice question 7, we have an object 5 centimeters tall placed 20 centimeters in front of a convex mirror. With a radius of curvature of 30 centimeters, we need to find the image's position, nature, and size. This slide is intentionally left blank for your working out. Next is question 8. An object 7 centimeters tall is placed 27 centimeters in front of a concave mirror with a focal length of 18 centimeters. We need to determine where to place a screen for a sharp image and identify the image's size and nature. This slide is intentionally left blank for your calculations. Now, let's explore the refraction of light. Refraction occurs when light travels obliquely from one transparent medium into another, causing it to bend. Light bends towards the normal when entering a denser medium and away from it when entering a rarer medium. This visual illustrates the concept of light refraction. When light passes through a rectangular glass slab, it bends twice, at the air-glass interface and again at the glass-air interface. The resulting emergent ray is parallel to the incident ray but is laterally displaced. The laws of refraction state that the incident ray, refracted ray, and the normal at the point of incidence all lie in the same plane. Furthermore, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant, known as their refractive index. The refractive index is a measure of how much a material slows down and bends light as it passes through it. This image highlights how light behavior changes when entering different media. This diagram further illustrates the principles of light refraction. This visual representation shows the refraction process in detail. Spherical lenses are transparent materials bounded by at least one spherical surface. Convex lenses are thicker in the middle and converge light, while concave lenses are thinner in the middle and diverge light rays. When rays parallel to the principal axis pass through a convex lens, they converge at the focus on the other side. Conversely, in a concave lens, these rays appear to diverge from a focus on the same side as the lens. In a convex lens, a ray passing through the focus emerges parallel to the principal axis. Similarly, for a concave lens, a ray directed toward the focus will emerge parallel to the principal axis after refraction.